L. So in the graph on the bottom right, you'll see XL bar is the line here. Okay, so this is the value we're going to determine. And if the X bar lies somewhere in this shaded area, we are quite confident to say that well, the null hypothesis is not correct. Okay, so alpha here to be the type 1 error, and this is the shaded area here. Okay, right, then it will become, well, it's a reject H naught given that H naught is true. This is type 1 error. It is true, but we reject. And it becomes the X bar greater than X bar L. And it becomes, we just apply the equations, minus mu and divided by sigma over square root of n. Okay, some arbitrary. And then on the left hand side, it becomes a standard normal distribution. So we use Z to denote it. Okay, so on the right hand side, it's the same. Okay, and then we can rewrite the right hand side term to be Z alpha. Okay, and Z alpha is actually something very close to this, right? Right, so given this, we can use standard normal distribution to answer this question. So we set a 5% confidence level, alpha equals 0.05. Okay, we get this value. Okay, from the last line, that's 2 lines, we get this. And Z alpha to be 1.645. We'll see the table in the previous slides, right? So given n equals 400, mu 170, and sigma 65, we plug these values into the expression on top left corner. We will get the XL bar to be 175.34. 175.34. Okay, so if we come back to this plot, XL bar here to be 175.34, and now X bar is actually 178, right? So 178 is greater than 175, so we can reject the null hypothesis. So we can reject. Okay, because at the moment, this XL bar is 175.34, but X bar to be 178. It's greater than that. So it's in the rejection region. It's in the rejection region. So we can reject. We can reject null hypothesis. Okay? So if we reject, it means that we prefer the H1, the alternative hypothesis is true. So it means that the mu is greater than 170. This is something that we prefer to have, so we can say this is expected to install the new billing system. Okay, so this is an example of collecting data, do the statistical inference, get the insight, and make the decision. Okay, so that completes the process with a very simply and statistical inference work. Yep. Okay, so this plot gives us the whole structure, right? The normal distributed behavior of the sample and the mu, right? Mu at 170, and XL bar to be 175.34 is here, and we collect data with 400 samples. We got the value here, so we reject. So there's a red cross on the null hypothesis, so we prefer in favor of H1. H1 is okay, is our accepted assumption. Okay, so this is the structure of rejection region approach. And we can further modify this into a standardized test statistic. Okay. Remember the normal distribution and standard normal distribution, right? We can standardize it so that these plots will become standard normal distribution with mean 0, and we use Z to denote the whole structure, right? And on the next page, we just apply this normalization formula we can create a z value for the corresponding x bar. Okay, so if we compare these two values, compare these two plots, okay, they are actually the same plot, same distribution, but the first one is normal distribution. The second one is standard normal distribution. Okay, for the standard normal distribution, we use z to tell the story. Okay, and since every normal distribution can be standardized into standard normal distribution, so in the following lectures we will use standard normal distribution only, because every normal distribution can be interpreted, rephrased as standard normal. Okay, and the way to rephrase it is just using this kind of standardized process. Okay, and this value alpha is 1.645 is the same operations as we did last week, right? And also the table we gave you earlier in the slides today. And the thing is, we have to transform or reinterpret the x bar value into our z structure or standard structure. Okay, so that's it. So we have x bar 178, and these values are the same. We can calculate the z value. And given the z value, we will, since z 2.46 is greater than the value of 1.645, then we reject. Okay? So this is one way to do the rejection. Okay? Right. So on the other hand, remember the second sheet in Excel, right? We are playing with lots of confidence intervals, right? Right, and some of the confidence intervals do not cover the mean, right? So it means that this is confidence interval is also another form of rejection region. Okay, it means that if you create a point estimate and then a confidence interval, okay, and if the mu in the null hypothesis is outside the range of your confidence interval, you may reject. You may say, well, based on my study, based on my sample, the null hypothesis is not in the range of my confidence interval, so I reject the null hypothesis. Okay. A confidence interval can be used as this kind of rejection region. We will talk about this further later in later weeks. Okay. That's a more detailed, more delicate concept. Okay, so we have understand all this. And then I would like to share with you the last concept today. Okay, it's called p-value. Okay, p-value is a most widely used statistical terms worldwide. And again, it's a controversial or misused. Okay, the American Statistical Association earlier this year and last year, okay, they make several announcements saying that people should stop using or should take more serious understanding about p-value. Okay, well, let me talk about this. P-value is a probability. The P stands for probability. So p-value is a probability of what? Of observing a test statistic at least as extreme as the one computed given that the null hypothesis is true. Okay? It means that if the null hypothesis is true, then the probability of getting the sample you have, the probability of observing such outcome you have on hand is p-value. Okay, so p-value is the probability of having the outcome, having this set of sample having this kind of statistics, given that the null hypothesis is true. Okay, so for every p-value, it must correspond to a null hypothesis and a null hypothesis testing setting. Okay, right. So p-value cannot stand alone. There is no such situation, such scenario that I have a p-value, but without null hypothesis. No, that's not the case. Okay, because p-value is defined as this. If your null hypothesis is true, then the probability of getting the sample, of getting the statistics you have is p-value. Okay, and at least as extreme as the outcome you have. Okay, so in this case of department store example, what is the probability of observing a sample mean at least as extreme as the one already observed, which is 178? Given that null hypothesis is true, null hypothesis is 170. Okay, so the formulation is here: P of probability of X bar greater than 178. Okay, again we use the normalization or standardization process. The probability PZ greater than 2.46. Okay, so it's actually the right end probability. If I have 2.46 here, then this is the probability. This is the p-value. Okay, so p-value is a probability. Is the tail probability of your sample if your null hypothesis is true. Okay, so p-value here is 0.0069. It's very small. It means that you have only 0.007 of probability to see such sample if your mu equals to 170. Okay, so it means that the probability is very low, right? So you can confidently say, well, the null hypothesis is incorrect, I reject it. Okay, so people, well, in statistical inference, we prefer small p-values. The smaller the p-value, the higher confidence we reject the null hypothesis. Okay? So we will see lots of p-values since now, okay, because this is statistics. So p-value of a test, okay, p-value is probability z greater than 2.46 is the red area on the right-hand tail of this normal distribution. And p-value, there are several thresholds, okay, 0 or 0.01 or 0.05 or 0.1, okay. 10 to the right is less significance, less evidence. Okay. So if we have a p-value between 0 and 0.01, and it means that we have quite a strong confidence to reject the null hypothesis. Okay, and if it's between 0.01 and 0.05, okay, it's a strong evidence. And if between 0.05 and 0.1 is weak evidence. Right? But these values are for reference only. Okay, that is because in the old days there's no computer, there's no calculators. Okay, so it's not very easy to calculate such p-values. Okay, so the statisticians create a table for z distributions. So typically we will refer to a table to find the reference values. And we will have a whole table for z equal to 0.01, or alpha to 0.01, and then for 0.05, and we just check the values. Okay, and why 0.05? Because it's 1 out of 20, and this is 1 out of 100. Okay, so these two values are typically sort of regarded as less likely to happen, 1 out of 20 and 1 out of 100. Okay, and it's easier to calculate for set up a table. Okay, and then so the interpretation of the p-value. Okay, so compare the p-value with the selected value of the significance level, which is alpha. So if p-value is less than alpha, we judge the p-value to be small, and we reject the hypothesis. Okay? So if the p-value is greater than alpha, we do not reject. Right. So, in the future, when you hear some people say, well, this p-value is small, you have to ask him or her, what is your null hypothesis? Okay, this is a very, very important question. You have to know the null hypothesis so that you can interpret the p-value correctly. Okay, we have lots of tests in statistics. Hypothesis in different forms, different uses, different scenario. Okay, and people will get lost in the interpretation of p-value if people do not understand its corresponding null hypothesis. This is very important. This is extremely important. Yeah, but especially when we proceed to the second half of the course in regression. There are lots of p-values in regression, and what does that mean? Okay, it means probability of having this event, having this sample, given that the null hypothesis is true. So what is the null hypothesis? Okay. Right. Take to the end. So, little example, quick example. Suppose a manufacturer of light bulb advertised that on average its long life bulb will last more than 5,000 hours. So to test the claim, a statistician took a random sample of 100 bulbs and measured the amount of time until each bulb burned out. So if we assume that the lifetime of this type of bulb has a standard deviation of 400 hours, can we conclude that 5% significance level that a claim is true? So the data is in an Excel file, XR11 and 35. So we can quickly calculate this. Okay, H naught, null hypothesis. Well, okay, the mu, okay, this is mu. Mu should be 5,000. Okay. And the alternative hypothesis is that mu greater than 5,000. We hope that is true, so we put mu greater than 5,000 as our alternative hypothesis. So we calculate the z. Okay, we use the standard normal distribution to do the hypothesis testing. X bar minus mu divided by sigma over square root of n. Okay, and the three values are known. It's given. And for x bar we just apply the Excel sheet, right, and we will get the result. Right, so this is, we have in column A 100 samples. Okay, and we calculate the mean, standard deviation, all the required statistics for this data. Okay, and then we can, the value of the z value is 1.62. So the probability, p-value of z greater than 1.62 is 0.0526. 0.0526. Okay, it's slightly higher than our significance level, 5%. So we can say there is not enough evidence to conclude that the claim is true. Okay? So mathematically speaking, the hypothesis testing is quite straightforward. We just plug in these formula and find the p-value. Okay, just 2 steps. And we got a sample, so you know x bar. Okay, and mu is the value in your null hypothesis testing, right? In your null hypothesis, and this should be known using sigma, and you know the sample size, and you will get this value 1.62, straightforward. And you know you're going to test if this value is corresponding p-value, right? We calculate z. In that case, it's 1.46. And what's the probability on the right-hand side of this point? And it's the p-value. So if the p-value is less than 0.05, then we will say, well, there is enough evidence to reject the null hypothesis. But if it's greater than 0.05, then we will say there's no enough evidence. Okay? So this is actually just 2 steps. 1 step and 2 steps. And we got the p-value. Okay, so we will say p-value is for reference only. Okay, there is no, it's not very wise to use p-value only to make decisions. Okay, we know how to calculate p-value, and we know the definition of p-value, and we have also know the limits or the constraints of p-value. Okay, p-value is just for reference. We know particularly when we have a p-value like this, 0.05 to 6, it's only 0.02 higher than this threshold, than the significance level. In this case, if we reject or not, in such simple case, we just have calculated the x bar to infer the mu, well, we may reject. But in some complicated cases, such as regression, we have to think more. And I will explain that when we talk about regression. Okay? Right, so this is the end of my talk today. We talk about sampling distributions, right? And we talk about statistical inference. There are 2 forms of statistical inference: estimation and hypothesis testing. Okay, the estimation, we have point estimation and interval estimation. Point estimation is using x bar to estimate mu, and we use the central limit theorem to know that if x bar will follow normal distribution, then we can use this property to create confidence interval. Yeah, so this is the interval estimation. And given that we conduct null hypothesis testing, okay, we have rejection region approach and p-value approach. Okay, they are actually talking about the same thing. Okay, so that completes the materials we hope to cover. In fact, okay, the estimation and null hypothesis, there are a lot more topics to deliver. Okay, usually each will spend 3 to 9 hours to discuss, and lots of them are mathematics and calculations. Skip it. Okay, they give you the concept first. Right, so that's all I have to say today. I hope you have some understanding. And then let's talk about the interesting activity next week. So basically we just 2 hours, okay, from 7 to 9. Okay, don't spend too much time here. And it's paper based. Okay, so you bring your pen and pencil, erasers, whatever. There's no specific need to prepare your computer. Okay, and if you need some calculators, it's fine. Okay, bring some normal, simple calculators. It will be enough. We don't have calculus. We don't have sine cosine things here, right? So don't use that. Bring the complicated calculators. Okay, and I prefer not to use the calculator on the mobile. Okay, so keep your mobile away. And the thing is that the materials we tested will be from lecture 1 to today. We're lecture 7 today. Okay, and we have one lecture skip. Not skip. We talk about the case, right? Talk about the case, and you've done the case. So perhaps some of the questions will from the case. So you've done analysis already. Right, so from lecture 1 to lecture 7, which is today, and it's open book. But you may bring only textbook or lecture notes. Okay, you may write something on the lecture notes, but well, it's open book. You can bring the materials with you. Okay, so the thing is, I'm not asking you to memorize all these things in your brain. Okay, it's too demanding. Yeah, and I don't remember all this as well, so it's not a good. But for 18, 20 years age, that's a requirement. But for you, it's not. Okay, so it's open book. You can bring lecture notes and the textbook. If you have purchased the textbook, you can bring it. If you would like to do some exercise as well, so textbook is not it's quite heavy. So that's it, I think. So for 2 hours from 7 to 9, okay, you will come to the company, and we will set the seat. We will arrange the seat for you. Okay, we will have the seat posted on the board. So you just follow this instruction to take your seat. Okay, and yeah, that's it. I think. Yeah. Any further questions? But make sure you understand the stuff I gave you, and also the Excel games we've been playing. Okay. Yes, questions? Okay. I haven't said any single question yet, so I don't know what kind of problem will come up. But normally, yeah. But from my lecture style, I'm not asking you to do heavy, tedious calculations. Okay, that's not my style. Okay, so relax.